Okay, hello physicists. Welcome to our February 8th? February 8th edition of physics. So we just finished our first exam. So I'm going to spend a little bit of time in this video talking about the exam. And then we're going to go into Unit 2. And Unit 2 is where we talk all about forces as opposed to just motion. And so we're not at the beginning of the semester anymore, but we still have quite a ways to go. And so it's good right now to take stock of what we're supposed to have mastered so far. So how did the exam go? Not great, not terrible. Most of you got a C on it. If C is average, that is to be expected. But if we're looking at B and above, we have about 9 people in the B and above category, about, let me think, 8, 9, 10, 11 in the C and below category. So that's about half and half. If you're in this category, if you're one of these people, I want to talk to you because I do allow test corrections for under 70 tests to bring you into this category. So I want us all to be in this category of C and above so that we can get our scores where we would like to be by the end of the semester. Okay, now there were some things on the test that I saw that I was a little surprised to see so many people miss. So these are things that I want to hit again in this video. Now, so there were problems, quite a few problems in the test that were just one-dimensional motion and one-dimensional accelerated motion. The question I put on your review that was like this was this one with the racing car where the car is at some initial time going at a speed of 10 meters per second, and then at some later time is going at a speed of 30 meters per second. So it's going slower here, it's going faster there. And I asked you how long this took. So I wanted to find, and then this was over a distance of 60 meters. So x minus x naught would be 60 meters. Alternatively, you could put just x naught equals 0, x equals 60 meters. And then it asks how long would this take? Well, there are two ways you could do that. All accelerated motion problems can be done with these two equations. So you could, for instance, find out from this first equation, you could solve for the time, stick that time into the second equation, and then you would have basically this equation, I believe. And so this one has x minus x naught, it's got v naught, it has v, it has t, and you would use this equation then to solve for the time it took. So the trick, as always, in this type of a problem is listing out what you know and then looking at what you have. And let's look at the test question that I gave you on this. Okay, it says a ball slows down while rolling up a slope. After 3 seconds have passed, the ball's instantaneous velocity on its way up the slope is 20 centimeters per second. So it's going up, 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 up. After 3 seconds, there's the time. Ball's velocity is 20 centimeters per second. After 8 seconds, the ball comes to a stop. Okay, so your ball starts out fast, it gets slower, and it gets slower, 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 stops. Okay, so part A asks, what's the magnitude of the ball's average acceleration from the 3rd to the 8th second? Well, you would go V equals V naught A times. Actually, I would not. That's maybe not the best way to do it. I think the best way to do it, you want to find A, okay? And if you are just looking for average acceleration, that is just going to be the final minus initial velocity over the final minus the initial time. So 0 minus 20, that's our final minus our initial velocity, over 8 seconds minus 3 seconds. So that's minus 20 meters per centimeters. These should be centimeters per second. Minus 20 centimeters per second over 5 seconds gives you minus 4 centimeters per second squared. So if you were looking for the magnitude of the ball's average acceleration, I guess it would be just 4 centimeters per second squared. But it's getting slower. And if the acceleration was constant while rolling up the sill, what was the initial speed? Well, you can simply use V equals V naught plus AT. And the final, if you just use this last time and this acceleration, you could go ahead and say that 0, the final velocity, equals V naught, which is what you want to find, plus minus 4, because it's slowing down, centimeters per second squared, times t of 8 seconds. Okay, so your initial velocity then is 8 times 4 is 32 centimeters per second. And then part C, how far did the ball roll up the slope during its full 8 seconds of rolling? Well, in that case, you can simply use your accelerated motion. It's my phone calling from Florida. I assume someone wants to sell me an extended warranty on my car or something like that. Okay, and then part C, how far did the ball roll up the slope during its full 8 seconds of rolling? Well, you can just use this equation. You want to find that final x equals x naught would be 0. V at the, whoops, let's just use, what am I doing? We don't want to use a fancy one. Let's just use our initial one here. V naught would be 32 meters per second times 8 seconds plus minus 4 centimeters per second, centimeters per second squared times 8 seconds squared. Okay, so that's how I would do it. So a lot of people had trouble with this problem, so I don't want to discount its trickiness. I do think, though, that this is the sort of problem that we were trying to build up skills to solve in this unit, where you're given a little bit of information and you have to extrapolate everything from this one model that we spent a lot of time developing over the last couple of weeks. So that one I thought was tricky, but okay as far as a test question. The one that I was a little disappointed on was the second one. We spent some time last week, Wednesday, on our review looking at this question. It says a bomber lying in level flight with a constant velocity drops a bomb before it is over the target, neglecting the air resistance. Which one of the following is not true? Well, this was the one that was not true. And all the other parts of this were true. And the main point that I wanted to get across with this was that the motion in the x direction and the y direction are independent. So if you have a ball that's thrown horizontally or a ball that's dropped, the motion in the y direction of those two balls is the same. The only thing that varies is the motion in the x direction for those two balls. The y direction motion and the x direction motion are more or less independent, and unless you give that ball some initial velocity in the y direction, it doesn't change regardless whether you're shooting the ball forward or just dropping it. So, how did this manifest in your test? Well, I asked this question: a bullet shot horizontally from a gun. Now, here's the story that I want you to see from this, is that if you shoot a bullet from a gun, it takes more or less this path. Okay? And the way that it's going in time, it's going to be going the same amount of distance each second. Okay, so something like this. And if you look at where it's going in height, it's going to be dropping like this, where each second it's moving further down because it's being accelerated by gravity. However, in the y direction, unless you give it some initial velocity, these two balls, the one that's just dropped and the one that is shot out of a gun really fast, their position above the ground is going to go in lockstep. Okay, so in this one, a ball shot horizontally from the ground strikes the ground later than one dropped vertically from the same instant, same point at the same instant. No, it in fact strikes the gun about the same time. Never strikes the ground. I was shocked to see that this was given by some people, but no, of course the bullet hits the ground. I should say, okay, it's possible you were thinking with your super smart physics brain and realized that if you shot a bullet fast enough, you could put it into orbit. Okay, but that doesn't usually happen with bullets that are just shot from regular everyday guns. Okay. Strikes the ground at approximately the same time as one dropped vertically from the same point at the same instant. Ding, 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 ding. That's the point I'm trying to make here. Travels in a straight line? No, it does not. It goes in a parabola. Strikes the ground much sooner than one dropped from the same point at the same instant? No, it goes the same. They hit the ground at about the same time. Okay, so to me, we've done a lot of stuff just talking about models of motion, defining what we mean by acceleration, defining what we mean by velocity, and stuff like that. But this is the one piece of physics content, something that you can actually test in the external world. And that's the only thing we've covered this whole semester, as far as I'm concerned, that's actually physics. So that's why I think this one is important. Okay, so the last one that I want to go over from the test is this idea of shooting a ball out at some angle and then splitting up your initial velocity into initial velocity in the x direction and initial velocity in the y direction. And then you go ahead and you find your position in the x direction, which is just going to be x equals v naught t plus x naught. and then in the y direction, where your y equals basically minus 1/2 gt squared plus v naught. And I should say, okay, the reason you're splitting this up into an initial velocity in the x and the y is that the initial velocity that you use here is in the x direction, and the initial velocity here that you use in the y equation is in the y direction, times t plus y naught. Okay, so all you're doing here is you're using your v naught x. It's going to be v naught times cosine theta. Your v naught y is going to be v naught times sine of theta, and then you just stick these into your x and your y positions, and then from that you should be able to calculate where on this trajectory you are at any point in time. So this is an earlier time, later time, and then once you hit the ground, the model stops working because you're not under that constant acceleration regime anymore. Okay, so I gave you exactly this problem on the test, where you have to go ahead and find your velocity vector, 40 meters per second times cosine of 60, 40 meters per second times sine of 60. Okay, so that's the first part, is where you're just finding the x and y components of this initial velocity. And then for part B, I asked you what's the ball's altitude after 2 seconds after its launch. Some people had, unfortunately, problems with my use of that word. So I do not want that to be the sort of thing that trips you up on a test. So please, 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 if you're taking this test and you don't know what I'm talking about, you don't know what I'm asking for. Am I asking for a speed? Am I asking for height? You know, that's not the sort of thing that I want you to miss credit over. Please just ask a question during the test. So on this one, for instance, altitude is just how high up it is. So you would just use this equation, you know, minus 1/2 times 9.8 meters per second squared, and then times 2 seconds squared plus, and then you put in this, your v naught y times 2 seconds, and that would be it. You calculate it, and you're all done. And this gives you how high up you are 2 seconds after the ball is launched. Okay, so the good news or bad news is that if you don't feel comfortable with this material, don't worry. You will have more chances to see it. Now, I say that's good and bad news because it's bad news because you don't get to just forget this material and move on to something new. Physics is cumulative. It builds on itself, so we need to keep this material near and dear to your heart. In fact, in future tests, this equation sheet that I gave you on the last test is going to be on the next test. Why? Because all of these ideas about acceleration and on are still going to be useful. We're going to use vectors extensively in this next unit. So if there's stuff on that you don't feel comfortable with still, it's really worth your time to, you know, come in, talk it over during office hours, whatever. However I can help, I will try. Okay. And as I said, if you have a 70 or below, please hit me up so that we can get some test corrections to try to get you up to a 70%. All right, so what are we doing today? Well, we have already talked a little bit about how to describe motion. we've talked about describing motion with the velocity of an object, with the acceleration of the object. Now we're going to go from describing motion to try to explain motion. And this has been a pastime of people for millennia. Aristotle, one of the great early philosophers and pretty good scientific thinker, had the idea that forces cause motion. So the natural state of things, in Aristotle's point of view, is for things to not be moving. And if you look around the room, you say, that seems about right. So if you want to get something moving, you've got to push on it. All right, so that's a very common sense sort of thought about how motion works. And when I say common sense, what usually we mean by common sense is things that we've been taught that basically work, that we inherited from the systems of thought that came from a long time ago. Now Newton tries the Newtonian way of thinking. Now Newton wasn't the first person to think this. A lot of this is just kind of a more systematic version of what Galileo said. But his claim, and the claim that we are going to defend in this course, is that forces don't cause motion. Forces cause acceleration. Now that's an important distinction, because what it means is that if something is going at a constant speed, if something's just moving along, it's not our job to explain that. What we have to explain is changes in motion. Okay, so we have to explain accelerations. We do not have to explain simply moving. In Aristotle's point of view, the natural state of things is to be hunkered down, not moving. In Newton's way of thinking about things, the natural state of things is to be not accelerating. And whenever you have acceleration in Newton's point of view, that means you have to explain it. You have to introduce a force to explain it. So just to put that in the way that you've probably heard it since, 7th grade, 8th grade, Newton's first law says that if no force acts on a body, the body's velocity cannot change. That is, the ball cannot accelerate. Now that's probably not the way you heard it put in 8th grade, but it is hopefully not the first time that you're hearing Newton's first law. So, just to hit it again, no force means no acceleration. So, no change in velocity means that the overall net force, that's the sum of all the forces on an object, is zero. And equivalently, another way to say that is that any motion other than simply moving at a constant velocity requires us to propose forces that cause this motion. Now I should say, if you think of yourself just sitting like I'm sitting in an office chair right now, we are going to have to introduce forces to explain why I'm, for instance, not falling into the center of the earth. Why? Well, because I do know that there is a force of gravity pulling me down. How do I know that? Well, jump up, you feel it. You feel your arm being pulled down if you hold it in your other arm. And the fact that I'm not moving then means that I have to introduce another force, and we call this the normal force, that's pushing up on me. Okay, so I'm not gonna hit that too hard today. We'll do that on Wednesday. But this idea that if a body's not accelerating, the total force on it is zero, is one that we really are going to need to tease out in detail. Okay, so here's an example that I think is pretty good. Let's say we have a pipe in this shape that's shown, and it's oriented so that it's sitting horizontally on a tabletop. Okay, so this is not we're not seeing something that's up and down. You're looking at it from above, all right? you're looking at the pipe from above. The interior of the pipe is smooth. A marble is shot into one end and leaves and exits the other end. Which one of the paths shown in the drawing will the marble follow when it leaves the pipe? Okay, so let's remember, what does Newton's law tell us? No force, no acceleration. Now, you might be thinking about this marble when it's going along this path. As it's going along the path, it's getting pushed by the walls of this pipe to keep following in the path. Once it leaves the end, though, the only forces acting on it are going to be the force of gravity pulling down and the normal force pushing up, but those are not going to be acting in this back and forth direction. So, in the back and forth direction that our marble that we're looking at, there's no force. So, which one of the paths shown has no acceleration? Well, it has to be the one where the ball is simply going straight, okay? So this is the path where it simply continues to go in the direction where it was going before the last force in the XY plane was applied. Any one of these other ones shows a path that is being accelerated. These are all being accelerated in a XY plane because the direction is changing. So if there's no force, there's no acceleration. So it has to be the one where the ball continues to go in a straight line. All right? So I just want to hit this early because I know that a lot of people, when they look at this, they want to think that you start curving, you continue to curve. But that is not what actually happens. If you try this out, you'll find that the natural way that mass wants to move is just in a straight line without acceleration. And so that's how we want to sort of retrain our intuitions for Newton's first law. All right, now Newton's first law is not terribly informative. Most of the rest of the course is going to be spent teasing out the applications of Newton's second law. And Newton's second law, I hope you've seen it before, but maybe you haven't, is F equals ma. And if you remember one equation from this whole course, it should be F equals ma. That is the key equation of the first semester of physics. And Newton's second law proposes that forces act like vectors and they cause masses to accelerate. So the net force, that means you have forces pushing in all different directions and you have to add them up like vectors. And in the end, you get some acceleration vector that tells you how the motion of the particle is changing, and that is caused by the force. So we have F, a force, is the acceleration multiplied by the mass. So what this means essentially is that if you have a really big mass, you put a force on it, it's hard to get it to move. If you have a little mass, it's easy to get it to, or I should say, it's hard to get it to accelerate. If you have a little mass, it's easy to get it to accelerate. A big mass is hard to get it to accelerate. And if you just look at this equation, it defines for us new units. Our force has to have units of acceleration times mass. And so the good units for force that we're going to use for the rest of the course are newtons. And a newton is a kilogram times a meter per second squared. Kilograms times meters over seconds squared. Now, what does this mean physically? It means that if you have a kilogram of stuff, so that's around 2.2 pounds of stuff, and you have a frictionless surface, so think like an air hockey table where the object is just like floating around. If you apply 1 Newton of force to that block for 1 second, you will have accelerated it after that second, and if you just let it go after that, it'll be moving at a speed of 1 meter per second. Okay, so 1 Newton causes 1 kilogram to be going 1 meter per second if you push it for 1 second. So that's what this means. A kilogram can go a meter per second if you push it for 1 second. Kilograms times meters per second per second. All right, let's take a look at a homework problem that you can do with this. This is, in fact, one that is on your next homework. It says a 500 kilogram rocket sled can be accelerated at a constant rate from rest to 1,600 kilometers per hour in 1.8 seconds. Okay, so this looks a lot like the types of problems you've been doing. And that is no mistake. So our initial velocity is 0 meters per second. Our final velocity, 1,600 kilometers per hour. And we're going to want to multiply that by some stuff to get it in meters per second. So for instance, 1 kilometer is 1,000 meters. And 1 hour is 60 squared seconds. Okay, I think that should be fine. It asks, what is the magnitude of the required net force? Well, net force is the total force acting on an object. F equals m times a. So you are given m as 500 kilograms. And if you want to find what A is, all you need to do is use V equals AT plus V naught. Oh wait, that's not a good one to use. We don't have T. We have a distance though. Let's look. We have a distance of, oh no, we do have a T, 1.8 seconds. Okay, we do have a T, so we can go V equals AT plus V naught. V naught is 0. So you can put in V, which is going to be this V that you're going to find in meters per second. You're going to have a T, 1.8 seconds, and then you find A. Once you find A, you know what M is, you know the mass, you know the acceleration. From that, you can find the force. And if you have kilograms times meters per second, kilograms times meters per second squared is going to give you newtons. 1 Newton is a kilogram times meters over seconds squared. Okay? So the magnitude of the required net force should be something in newtons. Now keep in mind, Newton's second law says the net force. And the net force means that you're adding up all of the forces acting on the object, and whatever direction that net force is the direction that the object is going to be accelerated in. Now, as we know from our last unit, acceleration is a vector. It has a direction. And for this to work out, we have to insist that forces are going to add like vectors. So here's a good example of this type of a story. This is just a back and forth problem. So the forces in the y direction are going to just all cancel out. You have a normal force pushing up. You have gravitational force pulling down. Let's not worry about those for a second, because we'll have plenty of time to worry about them later. It says the figure here shows 2 horizontal forces acting on a block on a frictionless floor. So you have 5 newtons this way, you have 3 newtons that way. If a third horizontal force acts on the floor, what are the magnitude and direction of F3 when the block is stationary and when the block is moving to the left with a constant speed of 5 meters per second? Okay, now first off, I need you to recognize that these two forces, we could represent them as vectors. So F1, for instance, I could write as 5 newtons times I hat. That means it's 5 newtons in the x direction. And F2, I could write, let's call that F1. F2, I could write as minus 3 newtons in the I direction. Why is it minus? Well, because it's pulling in the minus x direction over to the left. And so if I add those two together, I am adding like vectors. I'm adding directionally. All the vector components in the x direction sum, all the direction or the vector components in the y direction sum. We don't care about the y for the moment. So my F1 plus F2 is going to be plus 2 newtons in the I hat direction. Okay, now you probably already could see that 5 this way, 3 that way gives you 2 left over. All right, and so if you wanted to add an extra vector in here to balance out all of the forces so your net force is 0, you'd have to put in 2 newtons that way. Okay, so your F3 in this case would have to be minus 2 newtons in the I hat direction. Now, it says, what are the magnitude and direction of F3 when the block is stationary? Now, I think you can easily see that when the block is stationary, that means that you shouldn't have any forces pulling it to the right or to the left. So that would be our answer. So F3 plus F1 plus F2 would give you 0 newtons. That would be a no net force. Okay? Now, the thing that's a little bit less intuitive when you're starting on these types of problems is this idea of what kind of net force is needed for a constant speed. Well, remember, Aristotle would have said, if I'm going to have a constant speed, I probably need to put in some force. But Newton says, constant speed? I don't need any forces for that. This is still the answer. Because if I have a constant speed, that just means I have no net force. Now you might be saying to yourself, hey Cordell, why is it that when I actually push a box across the room, it slows down? Yeah, well, that's because there is a force that is going to be acting on that, the force of friction that's causing acceleration, is causing it to slow down. Okay, so I realize maybe not totally intuitive. Requires a little thought. Okay, so before I sign off today, I want to set up a more tricky type of problem with Newton's second law. Here's one where, as we know, Newton's second law is that F net equals ma. So if I want to find the acceleration on an object, I have to add up all of the forces acting on an object and divide it by the mass of the object, and that'll give me the acceleration. So here's a problem that makes this very explicit. It says 3 astronauts propelled by jet backpacks push and guide a 120 kilogram asteroid toward a processing dock, exerting the forces shown in 529. Okay, so we have F1, 32 newtons at an angle of, they give me that angle as 30 Newton, or 30 degrees. F2 is just in the x direction here. has a magnitude of 55 newtons at 0 degrees. And then F3 is down here. And this is pushing 41 newtons. And that is at 60 degrees. I'm going to write this in terms of my unit circle. So 0, 90, 180, 270, and then this would be 300 degrees. Okay, why am I doing that? Well, if I want to write my fx components, it will be f cosine angle. And then if I want to write my fy components, it would be f times sine of the angle. And so I can write out my f1, my f2, and my f3 all as vectors. Okay, so my f1 is going to be f1 cosine angle 1, comma, f1 sine angle 1. My f2 is just going to be f2 comma 0, and I can see that because it's oriented along the x direction. However, if you wanted to write this as f2 cosine angle cosine of 0 times f2 sine of 0, you would get the same thing. And then here we have f3 cosine of angle 3, f3 sine of angle 3, and that's why I put this as 300 degrees, is so that I could use this nice slick notation. And then if I want to find my F net, that's all of the forces, external forces acting on this block. What do? To get the x component, I'm going to add up all of these x components. To get my y component, I'm going to add up all of these y components. Notice one of these is going to be positive. One of them is going to be negative. And then it asks me for a magnitude and a direction of the acceleration. Well, what am I going to do? This block has a mass of 120 kilograms. Okay, so if I know the force in newtons and I divide it by the mass in kilograms, that gives me an acceleration vector. Okay, so if I take F equals ma, I take F divided by m, that'll give me the acceleration vector. How am I going to find the magnitude of that acceleration? I'm going to use Pythagorean theorem, x squared plus y squared, and then take the square root. How am I going to find the direction? I'm going to have to use my trig. Okay, so I want you to try this problem and the other problem for Wednesday. And I think it's a good idea to try to read through the other problems that you have as well, because that'll give you an idea of what you know, what you don't know. But just to hammer it home again, everything we're doing in this unit is just going to be F equals ma over and over and over with different forces. Okay? And in this Newtonian picture of dynamics, what we need to explain is why an object is accelerating. And we say if it's accelerating, there's a net force on it. And how do you find the net force? You find the net force by taking the vector sum, adding up the forces in the x direction, adding up all the forces in the y direction, adding up all the forces in the z direction, and there you go. So I'm saying it a little bit glibly. I know it's going to take a lot of work, but that's the basic idea for our next 2 weeks, all right? So good luck. You have a homework assignment that's up due next Monday. All right, thanks for watching. Good luck.